In this video, we're going to think about electronegativity. And so electronegativity is really asking this question: who's hogging all the electrons? So thus far, we've really talked about sharing and sharing equally. So we know that the electrons are shared in order to achieve octet. But if we look at things electrically, most of the time it's unequal. So if this molecule here is HF, and you were to put hydrofluoric acid in an electric field, what you will see is that your HF molecules that started out kind of all over the place, if you apply electricity, they will all orient themselves in the same direction. And so the reason they do that is because they have what's called a partial charge, which we have talked about before. So this partial charge is part of what's called a polar bond. So these have a partial charge. So this is partially charged, where this is delta minus and this is delta plus. So we have a slightly positive and a slightly negative end. And so if we were to annotate this and maybe not want to draw this large 3D structure, what we do is we can draw something called a dipole moment. And a dipole moment is a diagram of how polar something is, or it indicates that it is polar. So we're going to draw a little vector, and a vector is going to look like this, where it has a plus sign on one end and an arrow. So this points towards the negative. Oops. So the fluorine is more negatively charged because it has a higher electron affinity. So it is going to hoard the electrons. So we're going to draw it with a plus sign on the slightly positive and a negative sign or towards the F. So this arrow points in the direction where the electrons are. So covalent bonds are either covalent or polar covalent. And so there's going to be a range of covalent bonds and a range of polar bonds. And so we can start to predict if a bond is polar or not. And so we can do that, and we're going to be able to do that using this thing called, or this new periodic trend called electronegativity. Electronegativity is defined as the ability of an atom to attract an electron to itself. It's going to start hoarding the electrons. So electronegativity says it's going to try to absorb all the electrons. Because it's in part of a bond, it can't steal them like it can in an ionic bond. So electronegativity mathematically combines both the ionization energy, the electron affinity, the size, the effective nuclear charge, all of the periodic trends in a complex mathematical formula in order to say some elements have a higher electronegativity, so they attract the electrons more often. So the electronegativity trend, generally, if we draw our periodic table graphic up here at the top, it's going to increase as we go across and decrease as we go down. And you can see that in the graph attached below, where fluorine is the highest and francium is the lowest. So if we pretend we can't see this graphic on the right, and we attempt to arrange phosphorus, sodium, nitrogen, and aluminum in order of increasing electronegativity. So these elements are all in the same row, so we just rank them from left to right, where sodium is the least electronegative and nitrogen is the most, followed by phosphorus and aluminum. So we can rank these, and the difference between these is going to tell us about how they function in a bond, because electronegative atoms may or may not be electronegative in a bond. So electronegativity can predict polarity. So we're going to use the difference, well, the absolute value of the difference. So sometimes electronegativity is referred to as chi, the Greek letter X. So chi1 minus chi2, the absolute value, basically just make the number positive. and we can predict the polarity of a bond. So a covalent bond, or a nonpolar bond, has a difference of 0 to approximately 0.4. Polar covalent is 0.5 all the way up to 2.0, and an ionic bond is 2.1 all the way up to the greatest you can get is about 3.7 or so, 3.3. So these large ranges tell us that there's a differing degree of the strength of a polar bond. So the degree of polarity through a dipole moment. So when we think about this HF bond, we drew this annotation. And so that is the dipole moment. The dipole moment tells us to what degree or how much the electrons are brought from the hydrogen to the fluorine. And so we can measure this in dBi. And so this unit is dBi, is D, and we can measure that using this equation where mu is the dipole moment, Q is the charge, and R is the bond length. And so dipole moments can be measured, or we can calculate that. And so it's important to note that the charge of this will be in coulombs, and bond length will be in meters, and dBi is in a unit D, and so it is a conversion factor of 3.34 times 10 to the negative 30th coulomb meters equals 1 dBi. So this is a measurement that we can look at. We can also predict from the information in a bond structure, and we can start to think about how polar something might be. So for the HF bond, we know it has a dipole moment, and the bond length is 130 picometers. So if the charges are fully separate, which means instead of having HF just kind of lopsided, that's not a very pretty picture, but if instead of that, what we have is H plus and fluorine minus. So we still have the same charges, just in this case, it's +1, -1, instead of something that is delta minus and delta plus, meaning partial. Fully separate, what is the dipole moment? So if mu equals QR, Q is the charge on an electron, which is 1.60 times 10 to the negative 19 coulombs, multiplied by 130 picometers. And we need to convert that into dBi. So we are going to first convert the picometers of 1 times 10 to the 12th picometers and 1 meter. And then we need to convert into dBi. So 1 dBi is 3.34 times 10 to the negative 30th coulometers. And so when we plug this into our calculator, the dipole moment is 6.2 dBi. So this tells us it's a relatively large dipole moment if they're fully separate. So this is an ionic bond character. But using different mechanisms, we measured it to be 3.5. So we can calculate what the ionic character for the bond is. So it is the measured dipole divided by the ionic dipole multiplied by 100. So in this case, it's 3.5 divided by 6.2 multiplied by 100. And that gives you that it is 56% ionic. So this tells us that this bond is not shared, but not fully ionic. And so we can look at this measurement for lots of different bonds. The other thing we can do is try to identify each bond as polar, covalent, or ionic based on the electronegativities. So in this case, we're going to be able to subtract the two values. So for strontium and fluorine, those are a nonmetal and a metal. So we suspect that it should be ionic. So it would be 4 minus 1, that gives you 3, and that's ionic. For nitrogen chlorine, 3.0, minus 3.0. That equals 0. So that's covalent. What about a phosphorus-oxygen bond? 3.5 minus 2.1, 1.4. Polar. We can also look at a phosphorus-hydrogen bond of 2.1 minus 2.1, and that equals 0. So that's covalent. Some other ones we could look at are a nitrogen-oxygen bond, where we have 3.5 minus 3.0, oops, and that is polar. But probably just slightly, because we know that the line between covalent and polar is somewhere between 0 and 0.4, 0.5. So we can look at all of these different things and see that there are a wide range of the degree at which polarity occurs. So let's look at an example problem. So if the PO bond is measured to be 151 picometers, and the scientist measures the dipole to be 2.35, what percent ionic is this bond? So percent ionic is the measured value divided by the calculated value. So we need to calculate it what it would be if we had a fully, instead of a PO, in this case, we would have a fully separate P plus O minus. So in this case, we have mu equals Q R, which is equal to 1.60 times 10 to the negative 19 coulombs times 151 picometers. We need to convert picometers to meters and coulometers to divide. So there are 1 times 10 to the 12th picometers in 1 meter, multiplied by 3.34 times 10 to the negative 30th coulometers in 1 divide. So this gives us a value of 7.23 divide. So this is our ionic character. If they were fully separated at this length, this is what we would measure. So the ionic character is 2.35 divided by 7.23 multiplied by 100, and that gives us 32.5%. So this tells us that the dipole moment is not a quite ionic bond. It's only 32% ionic. So polar bonds are going to be really important for how these molecules function in 3D space. So when we think about the polarity, we want to be able to think about how these bonds come together.